Okay, so we're back again and we're looking at constant acceleration. So, last lesson we looked at displacement time graphs, and today we're going to be looking at velocity time graphs. Okay, so instead of displacement on the vertical axis, we're going to have velocity on the vertical axis. Before we get going, just a quick reminder of some of the definitions we've been using. Displacement is the distance in a straight line between where an object currently is and where it started. Velocity is the rate of change of your displacement, and acceleration is the rate of change of your velocity. So it's very important that we think about these as rates of change, and the notations for these as we covered before. Now I want you to really think about why I'm honing in on the phrase rate of change. All will be revealed. So here is a velocity time graph. If you notice on the vertical axis, we've swapped out displacement for velocity. So we're reading the speed at which the particle is moving. Okay, obviously with velocity, there's positives and negatives. So we're just thinking about the pace at which this particle is moving. Okay, so I was talking about the rate of change earlier, and the connection I wanted you to make is to the gradient. In pure maths, you found the gradient to be the change in y over the change in x. Well, here we've added some context to our y variable and our x variable. Our y variable is velocity and our x variable is time. So if we make that substitution, and we say that in this case the gradient is the change in velocity over the change in time, well, that fits perfectly our definition of acceleration. Acceleration is the rate of change of velocity over time. So our acceleration is going to be found by finding the gradient. If you have a velocity time graph, and this is the most popular graph that we'll be working with in constant acceleration, the gradient will be the acceleration. So let's go ahead and find the acceleration. So in this case, looking at part A, the change in velocity from the beginning of part A to the end of part A is positive 15. The velocity has gone from 0 to 15. The change in time is 10. It took 10 seconds for this to happen. So 15 over 10, that gets us an acceleration of 1.5 meters per second squared. Okay, we can do exactly the same thing in the other stages of this journey, and we can find the acceleration for each. Take the time to pause here and see if you can calculate for yourself the acceleration in part B, C, and D. And here's the answers you're looking for. In part B, we didn't actually have to do any calculations, as I'd want you to recognize straight away that the velocity has stayed the same for 10 seconds. The velocity has not changed over those 10 seconds. Acceleration is the change in velocity. If there's no change, the acceleration is 0. In part C, we've gone from 20 to 15, so that's a change of velocity of 10, and the time interval was also 10. The acceleration here, 1 meter per second squared. We can use a sense check here. In part C, the graph is less steep. The gradient of the line there is less steep. So I actually expected for the acceleration to be lower than the acceleration for part A. So as I'm working this out, it gives me some confidence. It makes sense that I got a lower value than I did in part A. And part D, a couple of things to point out immediately. We know that the velocity is reducing. So just be careful that you're doing this calculation in the correct order. We're going to take the final velocity here, which is 0, and subtract the original velocity, which was 25. That gives us the negative 25. That gives us the negative that we need within our final answer. The time interval here was 20 seconds, 50 minus 30, and we can calculate that to be negative 1.25 meters per second squared. So just be really careful on the negatives. And of course, negative acceleration we refer to as deceleration. The velocity is reducing over time. Okay, so apart from finding the acceleration for different portions or different stages of this journey, we would also be interested in finding the displacement. We don't have an axis for displacement this time round. Velocity and time are the two variables that we have. But velocity, time and displacement are all connected. We know from GCSE that we had a formula we could use: speed equals distance divided by time. Well, instead of speed, we're using the vector quantity of velocity. And instead of distance, we're using the vector quantity of displacement. So they themselves have a similar relationship. And this is a relationship you've already come across. Velocity is the change in speed over the change in time. If we were to rearrange this, we'd get an expression that says the displacement is going to be the velocity multiplied by the time. This will make most sense when the velocity is constant. So let's look at section B. We can find the displacement in those 10 seconds by taking the 15, so the velocity we're moving at, and multiplying it by the change in time, multiplying it by 10. That gives us a displacement of 150. I've basically found the area. This follows through for all other sections of the diagram as well. If I can find the area underneath the velocity time graph, I can find the displacement for that section of the graph. If I find the area under the entire graph, I found the total displacement for that journey. Okay, so we're going to need to do each section one at a time. If we look here, we can see some geometric shapes. Section A is a triangle. I need to use the formula for the area of a triangle. Section B is a rectangle. I'll use the formula for the area of a rectangle. Section C is a trapezium. I very much recommend you are using the formula for the area of a trapezium. Many people like to split this into two shapes, a rectangle and a triangle. In my experience, the students who get this question correct all the time are relying on the trapezium formula. Section D is also a triangle. Okay, so let's find the area of each of these sections, add them together, and we'll have the total displacement. So A is a triangle. I'm going to use half of the base multiplied by the height. So 15 times 10 divided by 2. That gives us a displacement of 75. We can do a similar thing for each of the other sections. In fact, pause the video here and have a quick go. Can you find the displacement associated with section B, C, and D? And here's what you should have got. So 150, 200, and 250. In part C, I've shown both ways how you could calculate it by splitting into two different shapes, a triangle and a rectangle, or the preferred method, or my preferred method, using the trapezium formula. I'll show you a little bit more about that in a second. And part D is just a triangle, 250. If we add together, the total displacement is 675. This represents the total distance travelled throughout this journey. It's important that we can describe what's happening at each stage of the journey, so I'll quickly throw that up on the screen for you. In section A, the velocity has increased from 0 to 15, and it took 10 seconds to happen. Because we have that straight diagonal line, we know that the acceleration is at a constant rate. If it was curved, it would be changing or a variable rate of acceleration. But these straight line segments let us know the acceleration is constant. In part B, not a lot has happened. The velocity has remained constant. It took 10 seconds to happen. We have constant velocity. The horizontal line here lets us know there's no acceleration. Part C, very similar to part A. The velocity has increased at a steady rate. The acceleration is constant. We can tell by the steepness, the gradient of the line, that part C isn't accelerating as fast as it was in part A. And in section D, we can see that the velocity is decreasing. we have deceleration. A negative acceleration value can be referred to as deceleration. Once again, we have that straight line, so we know the acceleration or deceleration is constant. So we've looked at a standard example now, where I've taken you through the nature, the structure, the features, and the interpretation of a velocity time graph. Let's see how this translates into some problem solving. In this question, we're told that a particle moves along a straight line. The particle accelerates uniformly from rest to a velocity of 8 meters per second. As soon as I know I'm working on a velocity time graph, I'm actually going to try and produce the graph straight away. Whether I'm asked to in the question or not, I'll start producing the graph so I have a good visual reference of the scenario. My y and my x-axis, velocity, and time. So once again, the particle accelerates uniformly from rest to a velocity of 8 meters in t seconds. So I know that acceleration is going to be positive gradient, straight line, diagonal. So here we go. I'm going to label off the velocity. I know that it gets to a velocity of 8, starting from the origin, a velocity of 0. And I know that the time it takes is t. So I'm just going to show this interval between the beginning and the end as t. Next, the question says that the particle then travels at a constant velocity of 8 meters per second for 5t. Well, I'm already at 8 meters per second, and if the velocity is constant, I should just be expecting a horizontal line for 5t. So those are the first two stages of the journey. We're then told the particle decelerates uniformly to rest, and it takes 40 seconds. So deceleration I know is aligned with negative gradient, and the time interval is 40 seconds. So here's my velocity time graph for the question that we've been asked. Part A of the question does actually ask me to produce this diagram, so it's good that I made a start on this already. In an exam, the main features that you need to represent in your diagram are firstly the shape. So in an exam, the examiner will be looking for positive gradient, horizontal line, negative gradient, and the labeling. So most importantly is probably the 8 meters per second that's been marked on, and then the time intervals along the bottom. And just to make a distinction here, these are intervals of time for the individual stages of the journey. They're not the time since the beginning. If I wanted to represent the time since the beginning, which is what we would really label on the x-axis, these 3 points would be t, so t seconds, 6t seconds, and 6t plus 40 seconds. So just be careful whether you're labeling an interval or the cumulative time up to that point. Okay, in part B of the question, we're told that the total displacement of the particle is 600 meters, and we're asked to find a value for t. So this unknown time interval, t. Well, we know that we can find the displacement or the total distance traveled by calculating the area underneath the velocity time graph. So S is going to equal the area of this shape, and I can see a trapezium straight away. Some people are going to see a triangle, rectangle, triangle, but for efficiency's sake, I'm going for the trapezium. Now, in a trapezium, we need to know and identify the parallel sides, and here they are. So I'm ready to substitute into my formula. The total displacement is going to be half A, which I'm going to take as the top side, which is 5t. I can see that by looking at the rectangle. The length of the base must be the length of the top. It's 5t. 5t plus, all of this together is 6t plus 40. So that was my highlighted lines added together, all multiplied by the height, which in this case is 8. Okay, just going to do some simplifying. 8.5, so the things outside of the bracket give me 4. And simplifying within the bracket gives me 11t plus 40. Okay, let's actually substitute the displacement. The question told me that the total displacement was 600. I'm going to carry on doing some rearranging from here. Let's divide both sides by 4. That gives me 150 is 11t plus 40. I think I can do this whole question without a calculator. Subtract the 40, divide by 11, t equals 10. So the unknown value of t in this case is 10. What I'll recommend to you is anytime you're working with a question like this, get an expression for the area, the total area, whichever shapes you decide to use, triangles, rectangles, trapeziums, get an expression for the area, put it equal to the displacement, and then just trust your maths and rely on your algebra, rearranging, equation solving skills to find the unknown variable. Okay, so just want to show you a table here that will help to clarify some of the different types of graphs that we're going to look at or have looked at. We have our displacement time graph, that was last lesson, velocity time graph, this lesson, and an acceleration time graph for those of you who get to some extension work. The quantities that we have are displacement, velocity, and acceleration. For all of these graphs, time is going to be the x-axis. Now, on a displacement time graph, your displacement was the y-axis. That makes sense. The velocity was the rate of change of displacement according to time. So the velocity was the gradient. In our velocity time graph, the y-axis was the velocity, the gradient is the rate of change of velocity according to time, and that is called the acceleration. So the acceleration was the gradient, velocity was the y-axis, and the displacement, as we've just seen, is the area underneath the curve. An acceleration time graph. This time round, the y-axis is acceleration. The gradient here isn't going to tell us much, but the area under the curve is going to be the velocity. So, in each of these, I'm sure you can see a pattern to this. We're working with displacement, velocity, acceleration. One of them is going to be the y-axis, the gradient is important, and the area under the curve is also important. Okay, so I think we'll stop there. You can do the pre-quiz and get off to some practice.